Welcome to the next lecture in our public lecture series. Some of you may have attended the World Year of Physics events, the Einstein play, the John Stachel's lecture about Einstein, and Steve Weinberg's lecture on the energy of nothing. My name is John Markert. I'm the department chair in physics here at the University of Texas. Before I introduce today's speaker, I'll ask you to turn off your cell phones or put them on vibrate or whatever you do under this situation. There it goes. So it's my great pleasure to introduce Harry Swinney, Sid Richardson Regents Chair in Physics and Director of our Center for Nonlinear Dynamics. Although not part of his official biography, I'll mention that he was born and raised in Louisiana most of his youth. Although he had a brief stint in Austin, at which time he attended Robert E. Lee Elementary, about 4 blocks from here. My son Sean attends that school now. Harry graduated from Rhodes College and went on to graduate work and got his PhD at Johns Hopkins University. And he held faculty appointments at New York University in the 70s and the City College of New York, where he was a tenured professor. His research at that time concerned phase transitions, critical phenomena. And in 1975, he conducted a famous experiment on rotating fluids, which was the first experiment to demonstrate the existence of what we now call chaotic behavior. You can maybe think of that as completely predetermined behavior, but completely unpredictable behavior. After that landmark experiment, chaotic behavior was observed in many systems throughout the world. In 1978, he came to the University of Texas as professor of physics, and he became the founding director of the UT Center for Nonlinear Dynamics. For the years where the U.S. News and World Report rated centers, this center was rated the #1 program in nonlinear dynamics in the country. He was a Guggenheim Fellow. He was in the American Academy of Arts and Sciences. He's a Fellow of the American Physical Society, a Fellow of the American American Association for the Advancement of Science. And in 1990, he was appointed to the Richardson Chair in Physics. In 1992, he was appointed to the National Academy of Science, and he was awarded the American Physical Society's Fluid Dynamics Prize in 1995. He is the author or co-author on over 250 publications, and he's given hundreds of invited talks, and his current research focuses on pattern formation, which will be the subject of his talk today. So please welcome Harry Swinney.
Thanks very much. I want to talk about patterns and how they arise in physical, chemical, and biological systems. Here are some examples here. I will use examples from our work here at the University of Texas particularly, and also examples from many other laboratories. But I want to first thank the students who've actually done the work here, students and postdocs and my colleagues on the faculty who have done these experiments. And of course, I must acknowledge those who supported the research, particularly the Department of Energy, Office of Naval Research, and NASA. And in Texas, we're fortunate in having some private foundations which support academic and research activities, the Welch Foundation and the Sid Richardson Foundation. Some earlier parts of this work was also supported by these agencies listed here. So let's first consider a fluid in a box that is maintained at a uniform temperature. So all the walls are fixed at a well-defined temperature. The gas in that box will be at that temperature. If we cool the box sufficiently, we get the formation of a liquid in the bottom of the box and a gas in the upper part of the box, separated by a line called meniscus. The temperature of the system is still uniform. And if we cool the system further, the liquid will solidify. If we had water, we would have ice here. But again, we have a system at a uniform temperature. There are seats up front here for people coming in. Now, this is not what I want to consider tonight, systems at uniform conditions, uniform temperature. I want to consider what happens when you impose a difference in temperature or other property. So suppose we have a fluid now in a box which has a uniform temperature on the bottom, which is hot, and a uniform temperature on the top plate, which is cold. If that temperature difference between the hot and the cold plates is small, we have heat conducted from the bottom plate to the top plate, but no motion of the fluid. Fluid remains at rest. If this temperature difference is increased, at a certain critical value of the temperature difference, we'll have convection, beginning with hot fluid rising in the center and the cold fluid from the top falling towards the bottom. So cold fluid coming down, hot fluid rising, so you have these convection cells. And however long the box is, could make it very long, you would have these convection cells ordered in an array. So we have the formation, spontaneous formation of a pattern where we had none before. Here we have an imposed temperature difference. We could also have a system not at a different temperature, but at a uniform temperature where we impose a velocity difference. Suppose the fluid is in a box with the top plate of the box moving to the right, the bottom of the box stationary. Then the fluid speed would change as indicated by these arrows. If the speed of the top plate was small, there would be no pattern. We'd just have the fluid speed varying from 0 at the bottom up to the value v at the top. But you know, if you move the plate very fast, you eventually get to a situation where the flow is very irregular. You get something called turbulence, as you would have in a stream where it's flowing fast. So there's a question that was considered by many of the great scientists early in the 20th century, whether it would be possible to predict when a pattern would form, when you would get some irregular flow of this fluid. And they failed in being able to predict the particular speed for this top plate at which a pattern would form, and even conjecture that it might not be possible, even in principle, to calculate the point at which a pattern would form. There was a British scientist, an Englishman by the name of G.I. Taylor, who said, let's consider something which is easier to build in the laboratory. Consider the flow between two cylinders that are concentric. There are seats up here, some seats, people back there. Two cylinders which are concentric. So let the inner cylinder here rotate with some rotation rate F, and suppose the outer cylinder is at rest. And the fluid is contained in the region between the two cylinders. For small rotation rates, no pattern forms. Taylor looked to see if there was a pattern by injecting dye into the fluid to see if it formed any particular shape. Now, the way people looked later to see if patterns formed was to grind up fish scales. And the fish scales would align with the fluid flow, and so you could see a pattern. But no pattern forms, you just see the whole region looks gray. But above a critical rotation speed of this inner cylinder, Taylor found that a pattern formed. The pattern consists of vortices. Now, they're pictured here. They're like a stack of donuts. They encircle the inner cylinder, and they're stacked up. And you can see the line between these vortices. Here's one vortex and the next vortex. So you have the onset of order, onset of a spatial pattern at a well-defined speed of rotation of the inner cylinder. Taylor did experiments with the outer cylinder rotating as well as the inner cylinder rotating. So on this horizontal axis, we have the speed of rotation of the outer cylinder, and here it's at rest. And on the vertical axis, the speed of rotation of the inner cylinder. And what he found was, as you go from rest, this would be the uniform state where both cylinders are at rest. If you go up with the speed of the inner cylinder, at some point you get these vortices forming at a particular speed of rotation of this inner cylinder. And the observation points are here indicated in red. This is the graph from his paper in 1923. He also did a calculation and predicted when the patterns would form, when these vortices would form, and he obtained these green points. And whether he kept the outer cylinder at rest or whether he rotated the outer cylinder. Here the outer cylinder would be rotating, and you go up in speed of the outer cylinder, and you see you reach a certain speed of rotation of the outer cylinder, of the inner cylinder, with the outer cylinder rotating at this speed, you reach a certain point where these vortices form. So with any speed of rotation of the outer cylinder, you always get the formation of the vortices at a particular speed of the inner cylinder. And the agreement between the observations that he made in the laboratory and the calculations he made is truly remarkable. When people thought there was not even possible in principle to make such a prediction of the formation of pattern, he made the prediction and found that it held in his observations in the laboratory to a very high degree of accuracy. So quoting from his paper here, he says, all previous attempts to calculate the speed at which a type of flow would become unstable have failed. Now, about 3 decades later, another Englishman was considering the possibility of pattern formation, and what motivated him was not the study of fluids, but interest in biology. And this person was Alan Turing, who's probably familiar to most of you here, for his work on the abstract computer. He's the father of modern computing, and he developed the idea in 1936 for the Turing machine. He's also well known for his work during the war. In 1943, he broke the German code. The Germans were sinking many of the British ships, and even though they were intercepting the messages from the Germans, they were not able to decode them. Well, he developed a technique for deciphering the enigma, the German code. So he's well known for that, but this is work that he did later where he was motivated to try to understand how patterns form in biological systems. How does a zebra get its stripes, or a leopard get its spots? So here is his paper that he wrote in 1952. This is the last paper he wrote. It's a classic paper in science. Before he died at the age of 42 in 1952. It was a tragic death, a great loss. But he says in this paper, and you can see from the title what motivated this work. Now, he was a mathematician. He didn't study a serious, complex biological system. He made a mathematical model, a simple model, in which there were only 2 processes. He had considered chemical substances that could react together and they could diffuse through tissue. So you have only reaction and diffusion, and that's it. And he said, by considering these processes, such a system, although it may be originally quite uniform or homogeneous, may later develop a pattern. So many years passed before the Turing-type pattern was actually observed in the laboratory. People attempted in different ways to pour chemicals together and observe a Turing pattern. And in the early 80s, in our group here at the University of Texas, we began to attempt to observe Turing patterns by pouring various chemicals together, and we failed for a number of years before we came up with a very simple device in which one could study Turing patterns. We got a patent on this device, and now it's widely used in laboratories throughout the world, but it's extremely simple. It just consists of a tank in which we flow some chemicals, some oxidizing chemicals, and the concentration of the chemicals in this tank is maintained uniform by stirring it vigorously. And we have another tank where we flow in reducing chemicals, and it's also maintained uniform. And the chemicals come into this tank and go out of the tank. These 2 tanks are not in contact with one another. They're separated by a thin gel layer. The gel is like Jell-O, something that doesn't react with the chemicals, but the chemicals from the upper tank can diffuse into it, and the lower tank can diffuse into it. Chemicals within each tank do not react with one another, but the chemicals in the two tanks would react in an oxidation-reduction reaction, and that occurs in this thin gel layer. So we can change the concentration of the input chemicals and look and see if a pattern forms in this layer. We look with a camera from above through the chemicals, which are transparent, and you can see the gel layer. And for most concentrations of the chemicals coming into these tanks, the concentrations in the gel layer is uniform in space. But we found for some concentration of the input chemicals, you can see a spatial pattern. Now this is a spatial pattern where the color represents concentration of one of the chemicals, the chloride ion, in a reaction. Now this is not the reaction that Alan Turing studied. His was a model system. This was actually a much more complicated system, but it's a convenient one for doing experiments. So we have a spatial pattern, and if we look at Turing's paper, he made a prediction about the spacing of the dots in the pattern. What's the size of the pattern? What determines your length scale? He said, in a process where you have only diffusion and some reaction, the size of the pattern, or the spacing between the dots, would be determined by the rate of diffusion of the molecules and by the reaction rate for the chemical reaction. So we could measure those independently and compute the wavelength for the pattern, and we got this value of 0.2 millimeters as the Turing wavelength, and this is actual measurement showing the picture. So this is a Turing pattern. Now, if it's a Turing pattern, it should occur at a critical value of the concentrations or some other parameter. Now, rather than varying concentrations in the experiment I will show, we varied temperature. At high temperature, the rate of the reaction is different than at low temperatures, but at high temperatures, you get no pattern. If you look down, you see uniform concentration. But as you lower the temperature, at a certain value of the temperature of this system, the pattern spontaneously forms. And here you can see this is the amplitude of the pattern, the brightness of the dots in the previous picture. So at high enough temperatures, in this case, high enough temperatures means something above 18 degrees Celsius. There's no pattern. The amplitude of the pattern is 0. As you lower the temperature below 18 degrees C, these dots appear, and they become more intense as you go down in temperature. If you go back up in temperature, they become faint and disappear at the same point where they appeared. So there's, again, a well-defined transition to a pattern. And here's another example of patterns in two other systems. Here we have a cross-section of a laser beam and an optical fiber. If the intensity of the beam is low, then the intensity would vary, looking across the beam, very continuously as you go across the fiber here. As you increase the intensity of the laser beam, at some critical value of the intensity, the beam breaks up into filaments. And if you look at these filaments, they're in the pattern that is hexagonal. And here's an example from biology where you have a vesicle adhering to a bilayer, lipid bilayer, and these are, again, dots which are in a hexagonal pattern. Here you see the length scale very small, 5 micrometers between the dots. Now, to determine when a pattern forms, one can consider this general procedure, which is what was followed by both Taylor and by Turing, although neither of them were thinking of it as a general procedure, they were thinking of the particular problems that interested them. But we could apply this procedure to many different systems and examine when a pattern will form. So we're interested in the situation when a system is not in a uniform state, but has some difference across the system, a difference in velocity or a difference in temperature or a difference in concentration, and we increase the strength of that difference or gradient. Now, for small differences, the system will remain uniform, but there is a critical value of that difference at which a pattern will spontaneously form. Now, what Turing and Taylor did was to solve the equations to get this uniform state and then consider what happens when there's a small disturbance of those uniform states. And they found if the difference across the system, say the velocity difference or temperature difference, was small, a small disturbance of that state, little perturbation, disturbance, would decay, would die. But above a critical value of the temperature difference of the state, if you drive the system far enough from its uniform or equilibrium state, the disturbance that's imposed will grow. So you consider a disturbance which is very small. Mathematically, it's infinitesimally small. So you can take the equations which describe systems, which are generally nonlinear deterministic partial differential equations. They're complicated equations because of the nonlinearity. But if a disturbance is small, the equation describing the growth or decay of the disturbance is a linear equation, can be solved straightforwardly. So this procedure, which has been appreciated in the last couple decades and applied to many systems, is now a standard way for finding when a pattern will form. And here are some other examples of patterns. They can have different forms. Here we have, again, in a chemical system, a strike pattern. This is a more complex pattern. It's called a quasi-crystalline pattern. It changes as you rotate the system, but actually if you rotate by 1/12 of a rotation and translate it in just the right way, move the pattern in the right way, the pattern reproduces. It's a quasi-crystalline pattern, and it's formed on the surface of a liquid layer, like a coffee cup. You shake a coffee cup up and down. At just the right strength of the shaking and the right frequency, you get this pattern form. And this was observed by some people in Pennsylvania. Now, the patterns don't have to be stationary or time independent. For some systems, when the patterns form, they travel. You have waves which travel. So here you have the core of a rotating spiral, and you look and you see this wave is traveling outward. This is a chemical system, a system which is about 1 inch in diameter, and this wave is propagating outward, and when the waves meet, they collide. And when they collide, they annihilate, they destroy one another. But you have these propagating